Okay, so I will proceed on. So, like I said, what we're going to use a shield for is one of the things we're going to use it. Let me start over. We're going to use a GPS receiver that's on that Adafruit uh, data logger shield. But we want to give you guys some background on what GPS does, how it works, what GPS actually is, so you can be, informed when you're using it. So, I mean, I think we are all much more familiar with GPS these days. Everyone has a GPS in their phone. We're all pretty reliant on it. But how does it actually work? You may or may not know, right? So GPS is the global positioning system. That is a U.S. constellation of satellites that orbit the Earth, right? There's several groups of satellites in multiple orbits, and those are the GPS system, along with a couple of ground stations and your receiver. So each of those satellites is in an orbit where it takes them about 2 days to go around the Earth. And what there's 6 separate orbital planes. So if you were to think of a sphere, right, there's like, you could have one on the equator, and then 5 other ones tilted. There's a picture later on, but basically all of the satellites are in one of those 6 orbital planes. That's what we mean by 6 orbits, and they're just sort of staggered on that single plane, such that you should always be able to see 6 satellites from wherever you are on the Earth. And then your receiver is going to receive signals from those satellites, and from that signal, from those combined signals, be able to determine where you are on the Earth. Right, so this is sort of what it looks like. It's sort of hard to show because you have all these basically circular spheres in 3D space, and you're projecting it onto an image. But right, you can sort of see here is like one orbit here, and there's going to be multiple satellites in that orbit. So each one of these ellipses or rings that you're seeing is a picture of the orbit, and then it's drawing the satellites on it. So currently there's 31 satellites that are operating. And the way that these satellites are designed to work is you have 6 orbits, and then you have 4 satellites in each orbit. So you have, and you call those those are called a slot. So that means there are 24 different slots. So 24 different satellites that are in orbit, but there's actual extra satellites because they always want to have extra, and if they have to bring one down for maintenance or something like that, they don't want the entire system to go down. So like we said, there's 6 of these orbits. They're at a fairly high orbit, so 20,000 kilometers. For reference, the International Space Station is about 450 kilometers. And it goes around the Earth in 90 minutes, right? Whereas these satellites are going to take 12 hours to make an orbit. So the entire system is operated by the U.S. Air Force, if you didn't know. Well, actually, I believe it's some combination of the Air Force and the Space Force now. I don't know exactly how those organizations interact these days, but so in 2011, they had this program they called Expandable 24. And basically what they did is on 3 of those orbits, they added an extra slot. So now the full constellation is 27 slots, but and they did that to increase accuracy and stuff like that. So, you know, the entire reason the GPS was originally designed is as a military tool, right? So, you know, World War II, the Cold War, those were basically a justification. The need to develop this military technology is where this money and motivation to do this research came from. So, so there were a bunch of predecessors that of different governments that were similar systems. You know, these had different names, right? And there's a few listed here. But like I said, the entire motivation for this was military needs. You needed first navigation for aircraft and ships. You wanted to be able to tell where you were, and then also later you know they found you could guide weapons with this, right? You could have GPS guided missiles and munitions. So GPS actually goes back to like 1973. So it's basically the Air Force for the longest time were the people in charge of the GPS. Like I said, now I believe there's actually some mix of the Space Force and the Air Force that runs it. And in particular, right, national security needs, i.e. needing to properly be able to launch nuclear weapons. So ballistic submarines, you know, which would be launching from some spot in the ocean, needed to know where they were to be able to accurately target their missiles. And then similarly, bombers and stuff like that, right? So, and this all goes back to, you know, the 70s. You had these guys, Roger Easton at the Naval Research Lab, Ivan Getting at the Aerospace Corporation, and Brad Parkinson at the APL, which is the Applied Physics Laboratory. The first satellites they launched in the 70s, you know, 1978, and basically the full constellation was in orbit in 1995, and then operational then. So in the 90s, up until a certain point, the civilian signal was basically purposefully degraded to give less accurate positioning. The idea being, well, people didn't really need it. This is a military technology, but we can give them a sort of a worse availability for it. That ended in 2000 during the Clinton administration. And they've basically, you know, since it's become so broadly used in the civilian sector, they don't plan to turn that degraded capability back on. Obviously, you want to restrict what civilian receivers are capable of. Basically, you don't want someone to be able to buy an off-the-shelf GPS receiver and use it to guide a missile. So there are actual limits on if you have a receiver. Basically, you can't have a receiver that can both operate above 18 kilometers and 500 meters a second at the same time, because that's basically a guidance system for a missile. So also, like 18 kilometers is higher than most of like your commercial, than most of your planes would be flying. So yeah. And then even if you are building these for a military capability, that obviously we don't want those getting shipped overseas. So there are State Department export licenses. That there's all these weird rules when it comes to software and hardware like this about where you're allowed to export it to. And in fact, most of your GPS units, if you were to get if you were to exceed those, so it's you have to exceed both of them at the same time, right? So obviously we're going to use a GPS unit that goes all the way up to roughly 30 kilometers, but we're not going to be going that fast. However, if we were at altitude and we did exceed that speed, the GPS receiver would basically cut out and stop telling you where you were. It would stop outputting information. So obviously other governments don't want to be dependent on the US GPS because we can and will just turn it off or encrypt it in different areas. So you have a number of compatible of systems designed by other countries, right? The Russian system is called GLONASS. European, the EU's version is called Galileo. Chinese is Baidu. Those three are the big other three that you will encounter if you're working with this kind of technology. And then Japan and India have their own versions, and they're somewhat developing them, or it's more restricted because those are smaller, or they don't quite have the need, or they're building it up. These days, just like you can buy GPS receivers, you can buy receivers for these other systems, and in particular the ones that are global, the top three, GLONASS, Galileo, and Baidu. And you can actually have devices that will work with all three of those constellations. And those are called GNSS devices, Global Navigation. I can't remember what the second S stands for, right? And what that lets you do is there's a lot, if you're using all three sets of satellites, you can figure out where you are faster. You can figure out where you are with better accuracy. And also if there's issues or maintenance with one of the satellite constellations, which is something that happens, you can still maintain a position. All right. So the question then comes is, how does this GPS actually work? And it uses a technique called trilateration. You may also hear it referred to as triangulation. So basically, each of your satellites is broadcasting a radio signal. And in that radio signal, they are giving their position and the time that they're sending that signal out. But by time, we mean very, very, very accurate time, down to nanosecond, and they use an atomic clock on board to maintain that time. And so what you do is you see the location that the satellite was at, and you see how long it took to receive that signal, because you see when it was the satellite transmitted. And from those two things, well, actually from the difference between when you received the signal and when it was transmitted, you can tell the distance from that satellite. It's, how quickly the radio signals traveled. They traveled at the speed of light. You know when you received it, and you know when it was transmitted, because that is what the satellite is telling you. So that gives you a distance from the satellite. So if I know how far I am from the satellite, I know that I am somewhere on this circle, right? Because all of these points are the same distance from that satellite. So if I repeat that process for multiple satellites, well, I know I have to be on this circle and this circle. So I have to be either here or here, right? I have to be at the intersection of these two circles. And if I had a third satellite, okay, now I know I have to be here because I have to be this distance from this one, this distance from this one, and this distance from this one. But actually, right, it's a three-dimensional picture, right? So instead of there being circles, they're actually spheres. And if I just have three satellites, I could be at this point or this point, right? Those are the intersection of three spheres. So I actually need a fourth satellite to get the actual position fix. So the GPS satellites get a time and location from the satellites. Or, sorry, the GPS receivers get the time of transmission and the location from the satellites. And then they compare those numbers from multiple satellites to figure out where their position is. If I only have a lock on three satellites, I can figure out my latitude and longitude because I know that I basically assume that I'm on the surface of the Earth somewhere, and that lets me figure out that fix. But because if I want actual 3D position, including the altitude, I need to see at least 4 satellites. And so it's called a fix. You can either be locked on to satellites, and if you have, which means you're accurately receiving their signal clean enough to figure out how far you are from them. And then if I can see that from multiple satellites, we'll call that a fix. So you can have either a 2D fix, i.e. I only know where I am on the surface of the Earth. I don't know how far I am from the surface. I could be at any altitude. Or I can have a 3D fix where I actually know my full position, latitude, longitude, altitude. But as you may recall, everything has uncertainty. So including the GPS. So there is going to be a accuracy or error on their location. And you may have seen this if you actually were to look at the output of your position and your altitude, you could see it, sort of bounce around. And where that comes from is there's actually a few different sources. There are clock errors, the actual atmosphere can cause errors. Just based on the geometry of the satellites or how they're arranged relative to you can cause errors. Obviously, the signal can be blocked, and your receiver is also going to introduce errors. So sort of a quick reference of how accurate your smartphone GPS is. It's roughly 5 meters. Obviously, that depends somewhat on smartphone model and all of that, but that's just to give you a rough idea. And, when you get near big objects, that's actually going to block signals. So that's going to cause your accuracy to get worse. If you were doing surveying or something where you really cared about knowing your position very accurately, you could get high precision GPS. Those are going to be significantly more expensive and probably require some calibration, but you can get a position down to the centimeter with those units. All right, so what is a clock error? Well, it's one, the clocks on the GPS are very accurate, but they still have some drift. And actually, a lot of that tends to come down to the actual quantum mechanics that they're using to measure the time. But in general, those can be minimized because the satellites can compare their signal with ground stations that are designed to maintain their clock as well. So they can actually correct their clock signals. So you don't have to worry about it like accumulating over time. Now, the clocks in the satellites are very expensive, highly engineered atomic clocks. The clock in your phone or in your cheap little $15 GPS receiver is significantly less reliable. So they're going to use something like a quartz crystal oscillator. And obviously that's going to be less accurate and it's going to potentially build up error. So that's going to be the primary source of your clock error. Another source of error is the actual atmospheric condition. The signal has to propagate through the atmosphere. And it's not a perfect vacuum. That radio signal is not traveling in a perfect straight line at c, the speed of light in a vacuum. It's traveling through something that has a slightly, different speed. It's pretty close, so you can get a pretty accurate reading. And it could get slightly bent, right? So it is just like water or a glass of the prism. It's a much less pronounced effect. But when you're trying to get super accurate positions, it will cause some slight error. So basically, the index of refraction and the speed of light through the actual atmosphere can vary slightly, and it can cause both the time to vary and it can cause it to slightly bend. Now, this picture is super, super exaggerated, right? It's not going to make these S turns over that sort of distance. But because you're dealing with such precision, it can introduce some error. And obviously, when the satellite is straight overhead, it's not going to bend at all, right? So that's where these errors are going to be smaller. But and also that's where you have to travel through the least amount of atmosphere. Whereas if I'm near the horizon, way over here, I have to travel through a lot more atmosphere to receive the signal. So there's more error that can accumulate as that occurs. Also, there are charged particles in the atmosphere. That's called the ionosphere. And this can cause GPS signals to get deflected. They can bounce around a little bit. And the actual conditions of the ionosphere vary, with time and with location. The monitoring stations, the ground stations, will actually monitor the ionosphere and make corrections, and you can remove a lot of it, but not all of it. And this particular effect, and the way they monitor this and correct for this is usually these effects are frequency dependent. So if you're transmitting on multiple frequencies, you can look at how the signal is affected on those multiple frequencies and then correct for it. So the actual, one of the important things is, pressure, density, and humidity of the air are going to change. And that is going to slightly change the index of refraction and the speed. So that means that's going to really introduce your error. And in this case, it's not really largely frequency dependent, so you can't easily correct for it. Also, the amount of water and other composition of the actual atmospheric gas is going to affect it. Water being the big one that changes the most, humidity at different points, clouds and stuff like that. So all of these are going to introduce small errors into the actual position. So one thing is, so once you start to get an error, you no longer have a perfect circle. And that can actually be amplified or reduced depending on where the different satellites that you're using to get a fix on are. And this is called geometric dilution of precision. But here's a quick example of it, right? So as soon as we have error in these circles, they don't become perfectly thin circles. They start to have this thickness with them, right? And if I'm using these two satellites, or I'm using two satellites, it depends how they're arranged. So if I have to be somewhere in this band and I have to be somewhere in this band, if they're like this, it's the overlap of those two bands is relatively small. But if the two satellites are like this, like one sort of on top of each other, I can be anywhere in this big green area because they overlap more. So that's what what we mean when we talk about that the geometry of the satellites can cause your position to be worse. And obviously, if I block the signal, it's I can't, if I can't see a satellite, I can't use that particular satellite to get a position. But even worse is the signal can actually reflect. So this is sort of the idea of shown here. Just think of these as buildings and you're standing in between them. And again, this is a very exaggerated picture because this satellite is many, many thousands of kilometers further away than any building. Right, but the idea is you're blocked from this straight line path that you're assuming when you do the position calculation. And instead, when you see the satellite, you're seeing it bounce off of this other building. And then obviously one thing that can occur is you can just be inside and not be able to see any satellites, which means you're not going to be able to see, figure out what your position is. So in this particular case, it's assuming that I'm actually this far from the satellite, but I'm really only this far from the satellite, right? And then also you can have interference from, radio transmissions. The sun can send out charged particles. That'll cause something called a solar storm, and that'll cause interference. And the Air Force will do maintenance on their satellites where they may have one stop transmitting or stuff like that. So that can all of that can lead to the actual signal that you're receiving not be as strong or as good and cause your position error to increase. And then the other thing is your receiver is probably the cheapest and simplest device that's involved in this, and it's of the lowest quality because it's the cheapest, and it is going to introduce some error. So, obviously you have to receive this frequency, and if you can only receive, one channel, that's less, and most civilian receivers are going to be like that. Obviously, so military receivers are going to be more advanced and also able to decrypt the encrypted channel. So they're going to be more accurate. And, as with anything, though, you start to get that technology trickle into the civilian models, but that's also going to become more expensive. So one thing that you can do is you can actually use differential positions. So that is what we talked about when I mentioned you can make corrections with the ground station, and that's called DGPS or differential GPS. And that's basically where you have a station on the ground that's at a known position because it doesn't move. And if you can see that one, you can actually make corrections to that. And that's going to give you very accurate positions because in addition to the moving satellites, I have this fixed station that I can see, and I know how exactly where that one is as opposed to these other ones. And that's, again, something you're going to use when you need super accurate position, like if you're doing surveying. So what does the GPS give you? Ultimately, it just gives you a location, but you can use that for navigation. We're going to use that for tracking the balloon in flight. You can use it for, mapping out landforms, and you can use it for surveying. One thing it's super useful for is providing accurate time synchronization between devices that are far away from each other. So if I'm broadcasting all these time signals over the earth, I'm basically creating a accurate clock that I can read anywhere on the earth. And that's going to let me very, very precisely synchronize two devices. Because otherwise, if I didn't have that, I'm basically relying on each device's individual clock. So I could synchronize them at one point and then send them far away from each other. But I'm relying on those clocks to maintain their time accurately. And, if it's you and me, I'm not building two atomic clocks that I can then send to different spots, right? That's a lot of money. That's a lot of technology. It's a lot easier to get a couple of GPS devices that are going to be able to provide a time signal down to the nanosecond accuracy. So what do you actually get out of these GPS receivers? So the GPS signal is received by the receiver, and then it'll output that in a format that's easily readable either by another electronic device or by a person by looking at the plain text. And that format is what's called a NEMA or NMEA sentence, right? Which stands for National Marine Electronics Association. And basically, each of these sentences is a string of text characters that is in a predefined format such that it will contain these particular pieces of data. They're going to be in a defined order, and there's going to be commas in between them. There are many, many different types. Like the 6 most common ones we're going to deal with are the RMC sentence, the GGA sentence, the GLL, DTG, GSA, and GSV. So these are all just, hey, the GGA sentence contains this particular pieces of data. It contains them in this order. And these other sentences are going to have different data. So you look at what data do you need, and then you figure out which sentences you actually have to monitor. So these have basically, they're grouped in, here's this type of information. And so these, of those 6 sentences, that's what these are. The RMC is the recommended minimum data. So it's going to have time. It's going to have some status information, latitude, longitude, your speed, track angle is your heading. So that's like degrees from north that you're traveling, and magnetic field information. GGA is the one that you're going to use most often because it's like a good mix of here's all the information that I need. Again, latitude and longitude. It's going to have information about the number of satellites you can see and what kind of fix you have. Most importantly, it's going to have the altitude, and then something called the height of the geoid, which is basically the difference between your local Earth surface and a idealized sphere. Like, obviously the Earth isn't perfectly smooth. So one thing that this is going to output is the difference between, hey, where's the surface of the Earth, and where compared to that if we were to treat the Earth as a perfectly smooth ball. So again, there's all these different sentences, and we're not going to go through them all right now. But you can look these sentences up in a reference and be like, oh, this has this information. So basically, what you're really going to need is what you're really going to do is going to be, oh, I need latitude, longitude, altitude, and date. So I need these sentences. Well, I need these 2 sentences most likely. So what these things actually look like is, so let's start with the GGA sentence. So if I look this thing up, I'll get a definition like this. And what this tells me is, here's the string, here's the formatting of all the different pieces, and then it'll have a table like this that tells you what's in each one of those. So all of these are going to start with a $sign and then have a 5-character string that tells you which sentence it is. And then they'll have all of the data. So that's going to be different from sentence to sentence depending on what's in it. And then it'll have a asterisk, and then it'll have a 2-character checksum that is going to be, basically that's a number that's calculated from the rest of this data so that you can tell that you accurately read in what the receiver sent. So this lets you check the rest of this data. So if you had an error in transmission and one of these values was changed, you would this checksum wouldn't match the rest of it. So it's literally a sum that you do on the rest of this data that lets you check that the data is valid. So I would basically, on the receiving end, recalculate the checksum, and I would get a different number and be like, oh, something happened in the transmission. So in particular, for the GGA, the first thing that you're going to get is the time, right? This is hour, minute, second. Then I get the latitude, right? I get a character for the latitude, in this case, north and south, right? Because I could do plus and minus, or I could do north and south. And in this particular scheme, I use an N or an S in this position here. I get the longitude degrees, and then I get an east and west. And then I will get basically a number that tells me how good of my fix is. And the lower the number, the worse my fix. The better the number, the higher the number, the better it is, largely. So I was asked, what does the number 9 stand for? Like in this particular string here, that WAAS, that's really a particular system. You're not going to see that on your GPS, but that's like a possible output. Like you can also see here's a simulator output because you can have GPS simulators. Dead reckoning really means that the GPS doesn't have a position fix anymore, but it used to have a position fix, and it knew how fast it was going and what direction it was going and how long ago it had a fix. So it's basically calculating a position based on its last known speed. Really what you're going to see is 0, 1, and 2 for the GPS that you're actually going to use. These other ones are more advanced, weird, more accurate fix types. You can see the number of satellites. You can basically, you have a number that tells you how inaccurate your latitude and longitude position is. And like we said, your altitude and the difference between that like perfect sphere and the actual surface. So one thing you will note, this has a time, but it does not have a date on it. So for that, we're going to need to use the RMC sentence. So if you're wanting to make a timestamp with both day and time and altitude, you're going to need to use both of these sentences. So this one in particular has a date. So it has day, day, month, month, year, year. But you'll notice it does have latitude and longitude, but it does not have altitude. So most often you're going to need to use both of these sentences. And by use, I mean, you can actually tell the GPS receiver which of these strings you want it to output. We'll get to that when we actually start programming with the GPS.